But the question over here is that benzene or aromatic compounds never undergo addition reactions. Why is it so? Let us see. Now, broadly, we have two basic types of addition reactions, that is electrophilic addition reaction and nucleophilic addition reaction. Now, if a nucleophile gets added to the aromatic compound, then what happens is that because nucleophile is an electron-rich species, so what happens is that the high electron density of the nucleophile an aromatic compound is unable to accommodate, due to which what happens is that rupture of ring takes place, and therefore we say that aromatic compounds never undergo nucleophilic addition reaction, because the moment nucleophile gets added to the aromatic compound, it causes the rupture of the ring. Therefore, it does not undergo nucleophilic addition reaction. Whereas if you see for the electrophilic addition reaction, in the preparation of RX from alkenes, it is the basically electrophilic addition reaction we have already discussed over there. In that, what happens is that a pi electron cloud of the alkene attacks on the electrophile gets added, and after that we have a formation of carbocation, and then basically a nucleophile gets attached on that positive charged carbon. So basically in a electrophilic addition reaction, what happens, you can say in a nutshell that in an electrophilic addition reaction, the pi bond is being broken and one electrophile and one nucleophile gets added to the compound. Now if similar thing happens in aromatic compound, what will happen is that one of the pi bond of the benzene ring will undergo cleavage first of all. Then what will happen is the electrophile and the nucleophile will attack on those positive and negative charge species. Then what will happen is that the electrophile and the nucleophile will get attached to the negative and positive charge sites in the ring. And therefore what will happen is that in the ring we will be left with the two bonds, and hence we say that the conjugation first of all has decreased. That means the resonance stability has decreased. And the second most important thing which has been affected in this process is that the aromaticity is being lost, because in aromatic compounds we do have 4n plus 2 pi electrons, that is Huckel's rule. So if suppose a electrophilic addition reaction takes place in a benzene ring, then what will happen is that a electrophile and a nucleophile will get attached to the ring, and during that addition what will happen is that one of the pi bond of the ring will be broken, and therefore now the pi electrons will be 4 only. So therefore 4n plus 2 equal to 4, that means n equals to half, which means that the aromaticity has been lost, and therefore it becomes highly unstable. So now you can say that with the evidences that if you carry out the electrophilic addition reaction in aromatic compounds, they lose their aromaticity and hence they become unstable. And also if you see it for the nucleophilic addition, it's again the same reason, that because of the high electron density of the nucleophile, the rupture of ring takes place. And therefore now we conclude that aromatic compounds, with the reasons that aromatic compounds cannot undergo addition reaction, be it a electrophilic addition or a nucleophilic addition. So that is only the one type of reaction which is being majorly shown by the aromatic compounds, which is known as the electrophilic substitution reaction. But here I have just said that majorly shown, that means aromatic compound do show another type of reaction also, which we term it as, it is nucleophilic substitution only. And in the aromatic compounds, when we have nucleophilic substitution, we again have SN1, SN2 types. But the major difference over here is that in case of the aliphatic halides, or you say aliphatic nucleophilic substitution, in the SN1 what happens is that it is through the formation of the intermediate known as carbocation, whereas in case of the aromatic SN1 substitution, it is through the intermediate known as the benzene, not the